Good. All right. So yeah, I guess this is kind of a little bit more on the theory here. So this is basically a bunch of the relevant equations. Some of these are just sort of different versions of looking at the same thing. So like this equation here is the same as this equation here. And yeah, like it's kind of color coded so you can sort of see all the differences. But yeah, this is just shorthand notation. So once we have our density matrix, we want to figure out the time evolution of that thing, and so that essentially means that we need to solve this guy right here. And so we can sort of reduce this into a like eigenvalue eigenvector problem, because like this is what we're after, right? It's equal to this, and that is equal to this, where these are basically our eigenvectors. And so what we're really going to be solving is this guy. Yeah.
Okay, can we stay on this slide a little more?
Yes.
To speak additional things. So the top blue box agrees with what William was teaching to us, right? So yes, evolution of density operator. And here in this limits, as it is shown in blue box, it is absolutely equivalent to Schrödinger equation, evolution of wave function. There could be translation one-to-one. And this deals with first level of quantum mechanics where all systems are assumed isolated. So if one creates a system in the excited state, in eigenstate, it will stay there forever. But there is a little cloud on the upper right. So the density matrix of the world is a direct product of the density matrix of our system of interest, which could be like a set of levels, and the density matrix of the rest of the world, which sometimes is called bath. Landon, will you please go to the very first slide, which we borrowed from Aaron's paper, with a nice picture? Yes. So the system is considered swimming in a bath in a sense that it's just a figure of speech. The system is immersed in a thermostat composed of the rest of the world. Okay, can you go forward to your...
Maybe. There we go.
Yeah, okay, thank you. And if we recognize that our system of interest is not isolated, not alone in the world, if it interacts with a thermostat, with a bath, then equation of motion for density matrix is not restricted with a blue term. It has an additional term which depends on density matrix of bath, which is green here, and interaction between system and bath in the second order, which is shown as V here. So this V is if the bath is the thermal motion of the ions in your molecular system. If the interaction between electronic primary system and the bath is non-adiabatic coupling V, then the equation of motion for density matrix, which includes combinations of orbitals, will include this term. And this term in brackets is equivalent to Redfield tensor that we worked on in previous meetings. So in a shorthand notation, this long equation can be stored as time evolution of density is Liouvillean dynamics plus Redfield term of dynamics. And this density operator can be replaced, can be expressed, can be cast in terms of a specific basis in the basis of basis functions psi I, psi j, and then the density matrix in the basis is density operator is composed as matrix times this basis set. So our problem of following the dynamics of density operator in a specific basis is a system of differential equations, where we have differential equation for each of these row ij. While for practical purposes, we are interested only when they coincide, row ii. But there is also very interesting science when they do not coincide. It's just too much for us. Now, we do have differential equation. We can technically propagate it by infinitesimal time increments and see how each of elements changes in the next time. But then it is numerically more demanding if, in case our L plus R operator, which was named like A capital in the first talk by payment, if this operator is time independent, then one can use the solution based on the eigenvalue problem. So one can find eigenvalues and eigenvectors of this L plus R supermatrix, and then compose the solution based on them. So the lower line shows how the solution is composed for a specific initial condition. Because if you do not care about the initial condition, then we have infinite number of solutions and we do not know which of them correspond to real life. Okay, Landon, sorry for interrupting. Please go ahead and continue.
And so this is kind of a breakdown of that equation that we were just talking about. So I guess this is that initial condition that Dimitri was just mentioning that actually, sort of solidifies our solution so that we have, the one particular solution instead of infinitely many of them. And then we're basically just, expanding that using all the other eigenstates, I guess. And I guess this is how we actually propagate it through time with this exponential here. Yeah, this whole thing, each of these terms just winds up being a particular expansion coefficient, like the C whatevers if you've taken like quantum mechanics classes.
So, yep. Go back.
Yep.
Let me add a comment. One more back. Yes. So let's look on the lower right blue box with eigenvalue problem. So now we connect back to the presentation by payment. So depending on the real or imaginary character of the capital omega of the eigenvalues, you have either oscillatory or experimental harmonic solutions or relaxing or exponentially growing solutions. So the L operator, Liouville operator, explicitly has imaginary unit, which means it is responsible for oscillatory solutions. And relaxation Redfield term, as we have seen practically in your numerical data, has only real values. So the density matrix here in our practical calculations is expressed in terms of eigenstates. And if it is in the terms expressed in terms of eigenstates, then Liouvillean dynamics do not change population. So if you focus only on the populations, all Liouvillean terms are dropped. And we have only R terms, which are real. So in our practical computation, the omega capital, the eigenvalues are real, and the dynamic that we observe is either exponentially growing or exponentially relaxing. Okay, Landon, sorry for interrupting you once again. Please go ahead.
Okay. So when we actually get into the file, I guess this is just a few input parameters that you should be aware of. So the time steps, you're going to want to set that to like however many of those, PXXX files that you have. And then you're also going to want to set the O min and the O max to whatever range of orbitals you're actually trying to observe. So like in this case, if we're trying to get data on like what would this be, like 30 orbitals roughly, then you'd set your O min and O max appropriately so that you're only looking at that range. Um, and so this is kind of part of the, some parts of the code where we're actually utilizing the Redfield tensor. So these are all like in order in the code also. So this is sort of where we first define them, and then these things are just straight up imports of the Redfield tensors. So basically, you're just looking at the conduction band here, valence band here. Then as the code goes on a little bit, we basically wind up setting everything below the main diagonal to 0, and that's just to I would guess disable thermal excitations, I guess. I'd have to think about that more though to actually be sure. And then we also we also wind up manipulating the terms along the main diagonal later on as well. And so this is sort of the Redfield tensor for electrons. We wind up diagonalizing that into the eigenvectors and eigenvalues, because those are what we're using to actually solve for the time evolution of the density matrix. And then we get these C terms, and then we wind up using those to solve for this equation down here. And this one also updates that same thing, and you can kind of see what all of the terms sort of are that we're using in this case. Yeah. And then otherwise there's just a bunch of stuff in here.
Okay, please, Landon, are you going to show anything else?
No, I do not have anything else.
Okay, then please join me. Thank you, Landon. So, any questions or challenges in the room? Any questions? Yes.
I guess I have one question on the second slide about the row bath term.
Okay.
So that's going to be a matrix, right? And then how would we go about determining that? I guess in a way, or estimating it.
Landon, please try anything you want or can, and then I'll pick up and continue.
I mean, I don't know off the top of my head how we calculate that one. So I mean, ultimately it comes from the nuclear motion, but I don't. Yeah, in the code, I guess I don't know how we actually get to that. Well, I mean, ultimately, I guess we sort of recast this equation into this form more so. So we kind of, I guess, go around it in a sense. At least I think.
Okay, yeah, thank you, Landon. Joseph, you are giving all of us tough questions, and they are right to the point. You were asking it at the end of the previous meeting when everyone left. So, by logic of these derivations, we assume that both system and path are quantized. So that any degrees of freedom are just set of quantum levels, which immediately contradicts to what we do practically, because our path, our nuclear motions are just sets of ionic positions which perform some motion. So we do it, it's a four-span argument. We cannot quantize 300 degrees of freedom. So if you do fair job, if you do everything as it must be, then each nuclear degree of freedom and each photon degree of freedom, each photon degree of freedom is just a set of harmonic oscillators, set of levels, multidimensional oscillators. And then those oscillators are considered to be like thermal buffer in the stove thermostat. So they consider to have low coherences of diagonal parts of the matrix, and Boltzmann factors energy to the power e to the power minus energy divided by temperature in the denominator. And then by combining this Boltzmann factor to the thermal buffer and interaction with electronic freedom, we will go relaxation of terms. If we have non-quantized point charge ionic motion, we do a lot of Boltzmann arguments. We need to artificially add either belts to promote relaxation only in one direction, or balance excitation and de-excitation. And there are several tricks. So this question is not easy. And what is shown here is abstract, ideal, and non-practical. Thank you for picking. Any other questions to Landon? On the chat line?
So Dimitri asks, what is psi naught and how is it composed? I believe that is the same thing as psi of 0 here. Or, well, yeah, rho really, I guess. Where did it show up?
Yes, here in this, we do not need to see anything else than this slide. The slide is excellent. So your matrix U is a matrix that composes all eigenvectors.
Yes.
And C, lowercase, is matrix of expansion coefficients, which are, yes, you're correct labeling. But what is psi naught? And if anyone is watching on the code, if you will not show it right now, maybe during the rest of the session, if anyone can pick up lines of the code that define psi naught, please do.
I can't remember if I grabbed that one or not. I guess when I was, nope, I didn't.
Okay, let me try from the top of the head, but it's better to show exact code. So,
well, I could just try to find it, I guess.
Yeah, just psi naught equals 2.
Got too much stuff on my screen. Something to do with the holes.
Yes, for electrons, let's move for this page. Okay, yeah, let's stay. Yeah, stop here. Very good. So these two lines, 184 and 185, makes build as a bridge towards the next few talks. So in the next few talks, we will all look on the importance of the input parameters IE and IH, which tell from which orbital we remove electron and to which orbital we promote an electron. And this PP and PPH, 1 means what is the initial density matrix, or segment of density matrix responsible for population at time step 1, which actually time equals 0. I don't know it. So the psi naught is the segment of density matrix at initial time, which has only one element equals 1 and all others are equals 0, which corresponds to populating only one orbit. I don't know whom to ask if the author of the question is satisfied because I asked myself. Landon, are you satisfied with this answer?
Yeah.
Okay, thank you. So more questions to Landon? Questions 1, questions 2, questions 3. But thank Landon.